Hi everyone. In this video, I'd like to talk about equivalence relations. So a relation R on set S is an equivalence relation. So an equivalence relation, I'm just going to underline that term. Relation R on set S is an equivalence relation if and only if it satisfies three properties: reflexive, symmetric, and transitive. So number one, reflexive. For all elements A in the set S, A is in R. In other words, A relates to A. A relates to itself. That's what it means to be reflexive. We will put up definitions for symmetric and transitive in a minute, but as we work through these definitions, I'd like to look at an example because I think it will help make the definitions a little bit clearer. So I'm down here in the example, and the example says S is the set of people in discrete math, so in our class, and R is the relation defined by A relates to B if and only if A and B have their birthday in the same month. So my birthday is in January, and if there's somebody in our class that also has a January birthday, then we would say I'm related to that other person. When I say related, I don't mean that we're cousins or brothers and sisters. I just mean related as in the relation R that we're defining here. Okay, so is it reflexive? Well, do I have the same birthday as myself? The answer is yes. This is reflexive. So for each person, each element in the set, for each person in discrete math, it is true that A relates to A. A relates to itself because a person has the birthday in the same month that they have their birthday. Okay, that was kind of a silly example, but you get the idea. Reflexive. Number two, to be an equivalence relation, we also have to satisfy property number two, which is symmetric. So symmetric basically says if AB is in R, then BA is in R2. In other words, A relates to B implies that B relates to A. It's commutative in some sense. So if I go back down to my birthday example, let's suppose that Mary relates to Bob because they both have March birthdays. Then it's also true that Bob relates to Mary, right? The order didn't really matter there. If we had an inequality or something else where order mattered, maybe we would say no. But in this example, we can ascertain that the relation is symmetric. All right, so let me get rid of my little scratch work there. The last property that needs to be checked is transitive. So transitive says that if A, B, and BC are in R, then you can transit A to B, B to C. You could go from A to C. I'll draw you a little picture here. So let's imagine you have, let me just make sure I've got a good sized brush that'll show up here on the video. Let's say you're here. And we'll call that point A. So if you can go from A to B, and you also know that you can go from B to C, then it's also true that you could go A directly to C. And that's what transitive is saying. It's like you can transit, you can hop along like you're a frog on a lily pad between the elements. And if we were to check this, you know, Mary has the same birth date as Bob, and Bob has the same birth month as Kathy, then it's certainly transitive as well. If you were writing this up for a homework assignment, you would want to include a few sentences to explain your reasoning. But I'm in the video and I want to be brief so that we can fit a lot of information on the screen. Okay, I'd like to do another example. So let me make some space here. So a different example. This one is a little bit more mathy, and I will get rid of some of the extra items here. Okay, so the question I have for you, we've got a set, S equals 1, 2, 3, 4, and we've got some relation that's given by all these ordered pairs. The question is this an equivalence relation? So let's go through and check, is it reflexive? So for each element in S, I need to check if each element relates to itself. So for example, the element 1, is 1, 1 in R? Yes, it is. Check. How about 2? Is 2, 2 in R? Yes, check. What about element 3? Does that relate to itself? Yes, it does. And the last element to check is 4, and 4 relates to itself. Okay, so the answer here for reflexive is yes. We went through and manually checked it. This is a very tiny set. The next question we want to examine, is it symmetric? So as I'm exploring the elements in my relation, I want to check that the mirror images of everything is in here. So 1, 1 is its own mirror image, and there's really nothing to check for these first couple of elements. Now we get to the element 1, 2, and if I'm looking at 1, 2, is its mirror image also in R? 2, 1 is there, so that's really good. Chugging along, we've got 1, 3, is its mirror image there? Yes, it is. We've got a 3, 1, 2, 3, yep, we've got a 3, 2. So the answer for symmetric is also a resounding yes. The last thing we have to check is transitive. Can we transit along as if we were a frog on lily pads? And I need to spell transitive. There we go. So for transitive, you know, the idea here is if we can match up the ending of one ordered pair with the beginning of another, like A, B, B, C, I better be sure I can go A to C. So there's not much to check here with the 1, 1, 2, 2, etc. But let's look over here where I get to 1, 2 and a 2, 3. Do I also have a 1, 3? And the answer is yes. You can go through and keep checking. 2, 1, 1, 3. Can I get 2, 3? Yes, it's also in there. So if you go through and check each of the pieces, it is true that this is transitive. What's remarkable when you get these equivalence relations is that they partition the set. So let me show you what that would look like. Hopefully my pen will behave here as it's been a little bit squirrely on me, but let's see here. So I've got my set. This is set S. And as I label the points in my set, I've got a 1, I've got a 2, I've got a 3, I have an attempt at a 3, let's see if I can get it to behave, and I've got the element 4. I know that 1 relates to 2, so those two items are in the same equivalence class because they're related. They're similar in some sense. They're in the same category. Also, 2 relates to 3. So 1, 2, and 3, they are in their own equivalence class. They are all related to each other. I can hop around, I can transit among those elements. Those are in the same equivalence class. 4 is in its own equivalence class. So I have 2 equivalence classes here, and you can see what this equivalence relation did is it carved up or it partitioned up the set S.